Good morning and welcome back. Because of the outbreak of the novel coronavirus, we will enter a distant learning system that is a remote educational system. I will record my educational materials, videos, and upload to YouTube so you can study at home. First, we will introduce Chapter 9, Irradiating Systems, Multiple Fields, and Radiations. In this course, many chapters discuss the EM fields. So I will give you an overview of chapters on EM waves. Last semester, Chapter 7, we talk about EM wave. But at that time, we do not consider the source term, no source term at all. And no source term, so no source term. We consider the simplest case, wave equations only, in a uniform space. And this space is unbounded. Okay, that's the simplest case. So maybe I can draw for you, such as last semester we have the incoming wave, sinusoidal incoming wave, propagating in the space. Sorry, it's not really sinusoidal. So this is the simplest case in material epsilon and mu. Okay? And we also consider the behavior of wave between two material. For example, the incident wave and transmitted wave. And reflected wave. One epsilon 1 and mu 1 and epsilon 2 mu 2. So in order to match the boundary conditions, we will generate reflected wave as well as transmitted wave to match the boundary condition. And we also consider many possibilities such as normal incident, oblique incident. And at that time, oblique incident is separated into the field, electric field perpendicular to the plane of incident, and electric field parallel to the plane of the incident. Now, last chapter 8, once again, we do not consider any source, and we consider a uniform waveguide of infinitely long. So we consider uniform waveguide of infinitely long. So just consider rectangular or cylindrical waveguide. Here, let me show you a rectangular waveguide, infinitely long. So do not consider the source term, just the wave only. The wave will propagate inside, and the boundary is confined with conducting material. Okay, so just like waveguide and cavities. In this chapter 9, we will consider source. I don't tell you where is the source come from. It's just a prescribed source that is caused by someone prescribed source, such as an antenna, a source, current source or charge source, sinusoidal, and again, we use an outgoing wave to infinity. Okay, in chapter 10, we will consider source again, but this source will induce electric field, electric dipole or magnetic dipole on metal, dielectric, and different materials. So this dipole source will become a radiation. These dipoles will become radiation source. Okay. We will cover chapter 11, but chapter 11 is special relativity. It do not cover wave. It talk about wave, but just the transformation between different coordinates. And in chapter 14, we will consider moving charges. So the charge can move in a space, and such as the synchrotron radiation, and we consider an infinite space. So because of the difficulty, in the latter 3 chapters, we will consider no boundary at all, no boundary. Simplify the problem. Okay. Next page. So what's our strategies? We will consider the source term. But before we consider the source term, we have to have a closer look at the radiation without source term. But we will consider spherical wave and cylindrical wave in a waveguide, cylindrical, without source. First is the spherical Bessel function. We will consider spherical wave solutions of the scalar wave equation. Spherical wave solution means the solution can be exist in the spherical coordinates and propagate to the infinite space. And scalar wave equation. The wave equation should be a vector. Why we say it's a scalar? It's a simplified system. We will consider Ex, Ey, Ez, or Bs, By, Bz, all other terms. So let's call spherical wave equation simplified wave equations. And we will consider Bessel functions and Hankel functions. That's the solutions. Although these chapters deal with the radiating system, we will first solve the scalar source-free wave equation in the spherical coordinate system. The purpose is to obtain a complete set of spherical Bessel function and Hankel functions. This complete function set, Bessel functions and Hankel function, can then be used for the behavior of the source as a complete function set, with which we will expand the field produced by the source. So the scalar source-free wave equation, if you don't remember, please check chapter 6, equation 32. This is a scalar source-free, time-dependent. It depends on the position and depends on time. And we know a time-dependent wave can be a superposition of its harmonic components. That means we can consider one frequency at a time. So from time-dependent wave, source-free wave equation, we can change to time-independent source-free wave equation. Each Fourier components satisfy these equations. So we got the Helmholtz wave equation. It's a time-independent source-free wave equation. So we call Helmholtz wave equation. What is the difference? We substitute this one into here, and no time dependence. Time dependence just here. So after double differentiate twice, we got minus omega squared. Minus minus become plus omega squared divided by c squared. So it's k squared. So Laplacian plus k squared times phi. That's the Helmholtz wave equation. What's next? Let's consider Helmholtz wave equation again. And we will use a spherical coordinate. So Laplacian here can be written as this form. R dependence, theta dependence, and phi dependence, plus the last term k squared times phi. Okay? So how to solve these equations? R, theta, phi. How to solve this equation? Our old friend, separation of variable. We define the psi into 3 parts, time together. Okay? UR is R dependence only. P theta depends on theta. Q phi depends on phi only. We can do that because infinite space, no boundary. We have any symmetry, so we can do that. If it is confined in some kind of special geometry, probably we cannot do that. In general, we cannot do that. Okay? So by substituting this equation into here, we got PQ the same, UQ, UQP, UP, UPQ, and this part depends on phi only. This part depends on theta only. This part depends on u only. So we change from partial derivative to total derivative. Okay, so it's a k squared UPQ. Next step is we can multiply by r squared sine theta squared because of these terms, and divided by UPQ. By doing so, this term becomes sine squared, right? Sine squared 1 over u. Because of this one, PQ cancel. The r squared, the u, the r, plus k squared, r squared, k squared, r squared. So we have r squared sine theta squared here, come from here. Okay? So this part depends on r only. And this one, 1 over p sine theta. Sine theta squared, sine theta. Makes sense. And sine theta here, dp over d theta. Plus last term here. 1 over q, dq squared, d phi squared equals 0. Okay, the simplest case is this term. The only terms with phi dependence. So these terms must be a constant. Let it be minus m squared. These terms should be decoupled from the other terms. So it must be a constant. Must be a constant. Okay? So, but the problem is y is minus. It's minus because we know it's azimuthal symmetry. So it not azimuthal symmetry. It's minus because we know if we change 2 pi 360 degree, the physics is still the same. We change 720 degree, the same. So it must be some kind of sinusoidal, sine or cosine, not exponential growing or exponential decay. That's why we have a minus sign here. Okay, how about the others? This part depends on R only. So we can assume the solution for this one is L plus 1. Why? Because this part, we know it should be very easy. It should be associate Legendre polynomial. So in that case, it's associate Legendre polynomial. We know this part should be, it equals to this part times this one minus this one. This is an associate Legendre polynomial. We are going to use these properties. We will divide in all terms by sine theta squared. We see that this is the only terms with R dependence. So it must be a constant. Let it be L plus 1. That's from our experience. Last, as in section 3.1 of lecture notes, we know this part, we have two solutions. We have the first solution is PLM, depends on cosine theta, and QLM also depends on cosine theta. And this terms normally becomes 0 because it is rejected because the divergence at theta equals plus and minus pi. Q here, easy, exponential im phi, exponential minus im phi. PQ can be read into a spherical coordinates, spherical harmonics, YLM. So it's a spherical harmonic. We talked about spherical harmonics before. Okay, so we can rewrite this equation, this Helmholtz wave equation, time-independent source-free wave equations, into spherical coordinates, and by separation of variable, separate this part, and this part. Eventually, P and Q has a simple relations. Let theta and phi has simple relations here. Let's move on. We still have R dependence. R dependence is not that easy, but still okay, acceptable. R dependence, let's write it into this form, equals L plus 1U. Let's rewrite U again as FL because this one U will associate with the value of L. So we can rewrite U as function F, but with subindex L. It's function of R. We just rewrite this equation again. So this part give us FL. So what else? K squared comes from here. We divide it by R squared. When this one works on this one, give this one. When this one give us 2 pi R plus so we have 4 terms. 1, 2, 3, 4. Okay, the first term, this one with this one, Second term, this one with this one. Third term, this one divided by r squared. And last term from here to here. So positive to negative. That's equation 9.81. Let's rewrite this equation again. If you don't like this one, you can write u here, and then u can redefine into here. Okay? And you can redefine FL equals 1 over r square root of r times u, but this time it's not the uppercase, it's lowercase u and with subindex L here, function of r only. And what else? FL. Others are the same, no difference. No difference here. But by doing so, UL will become this one. And as you can see here, that's the major difference. That's the major difference. Because of these terms, we change from this dependence can be moved out. You can do by yourself. You can double check by yourself. It divided into two parts. And by substituting these equations, we can rewrite this one. So this is a pretty good practice for you. You should practice right now from here to here. A simple derivations. It can be considered as an extra bonus. Proof that this one can be derived from this one. Okay, so you can consider it as a extra bonus for 1 point. Okay, let's move on. So UL, function of R, can be rewrite into Bessel function and Newman function. It's R dependence, but also can be expressed as Bessel function of fractional order, not integer, but fractional. 1 over 2, 1 over 3, 1 over 3 is fractional order. So FL in this time becomes 1 over square root of R times Bessel function L plus 1 over 2 KR and another one. We can define another symbol called C O N. C uppercase, C lowercase. Okay, N is lowercase, N uppercase. That's called spherical Bessel functions. Spherical Bessel functions. So spherical Bessel functions do not spherical Bessel functions are associated with the R dependence, not associated with other notations. And define Hankel function. Spherical Hankel functions is just a linear combination, or we can write in this form, or another one. H1, the first, and HL, second. JL plus INL, KR. HL, the second, equals JL, KR minus I. Looks like sinusoidal. Sine plus I cosine. Cosine plus I sine. Cosine plus minus I sine. Something very similar. Similar in some sense. So now, the Helmholtz wave equation, the solution for this one, will be ALM to be determined times HL1 here. and ALM second order times HL coefficient to be determined times YLM depends on theta phi, and this one depends on R, and K is defined as omega divided by C. C is the speed of light. Okay, most of you do not have any idea about this spatial function, so I will show you what is this spatial function looks like. Pictorial view. Maybe I should move on to here. First, so I just mentioned J and N looks like sinusoidal wave. However, J0 close to x equals 0 equals 1. It looks like sinusoidal. And N from here looks like sinusoidal, but be careful about this one. Okay, let's call spherical Bessel function and Hankel functions. Okay, I will review what we have learned about in chapter 7, chapter 3.7. Chapter 3.7, we talk about Laplace equation in cylindrical coordinates. Okay, and at that time, we deal with the Bessel function. So I will compare the difference between these two equations. Okay, so first, let's express Laplacian phi x first. And once again, separation of variable. Separate into three parts. First one is z dependence. That's exponential plus and minus kz. In this case, not here is not plus, but a minus sign. Because in these structures, it's just changed in z. So we have a minus sign here, unlike phi dependence. And once again, phi dependence, we have a plus notation here. So q will become exponential plus or minus I mu phi. Okay? And rho dependence, this one here, and what else? And these two, this one give us k squared, and this one give us minus mu squared divided by rho squared times r. Okay? Now it's constant to be determined, and rho. So r must be function of rho and k and mu. So the solution will be simple. R is functions of j mu k rho, k times rho, and we have Bessel function and Newman functions. That's the Bessel functions of the first kind and Bessel functions of the second kind, respectively, just like the previous case. So here we have the general solution can be write into Bessel function of the first kind, Bessel function of the second kind. It depends on mu here as mutual angle. Depends on k here. Z dependence, exponential decay or exponential growing. And this is the phase dependence, phi dependence, and this is the z dependence, separate into three parts. And remember, at that time, if we can rewrite this equation, we can rewrite a symbol called x. X equals k rho. The equation for R takes the standard form of the Bessel functions. So by doing so, we just divided by k, divided by k squared, k rho, divided by k squared give us nothing, k rho squared. So R now is function of x. So by doing so, the solution of Bessel function and Newman function, Bessel function of the first kind, Newman function, Bessel function of the second kind, we can then define the Hankel functions. Very similar, very similar. Okay? We have the Hankel function of the first kind, Hankel function of the second kind, J mu plus I n mu x, J mu x minus I n mu x. Okay, I will stop here. Let's in chapter 3. Now let's go back. This equation, we have Hankel function of the first kind, Hankel function of the second kind, but it's a spherical Hankel function. Spherical is slightly different from the previous equations. The indice is fractional, not an integer. And we have these terms as well. And this part is quite similar. Hankel function of the first kind, Hankel function of the second kind. Okay, so spherical wave solutions quite similar to Laplace equation. Laplace equation in cylindrical coordinates. Quite similar. So this gives you a better understanding of these special functions. Okay, we talked about this part in chapter 3 last semester. Now let's move on to the second part. Okay, just a moment. Maybe I should show you what is the function. What does it look like? Okay, this is the spherical Bessel function, J, spherical Newman function, N, and here, 0 looks like this one. 0 looks like this one. And you can check everything. So JL can be read in this form. HL can be read into this form. That's a spatial dependence of spherical waves. Okay, just have an impression. Quite similar to Bessel function and Newman function. The lowercase symbol, spherical Bessel function and spherical Newman function are quite similar in the expression and quite similar to Laplace equations for cylindrical coordinates. What's next? I will stop here for a few minutes so you can think about it. Compare these two figures. Okay? Not exactly the same because L here. Okay, L here is actually correspond to JL plus 1 over 2. So not exactly the same, but very similar in form. Okay, what's next? Next one, if we want to consider source term, no matter its current source or charge source, we will introduce our old friend, Green's function. Green's function. So we will consider another one, Helmholtz wave equation, but this time we will consider a delta function source. Therefore, once we can solve this equation, and then we can solve the Green function. And this one, we can use these properties to calculate all the source. How to do that? Looks simple, but actually it's not that easy. Before, we do not consider this one. But now, we will consider a value k-squared. The solution of the Green equation, this one, is given by this one. So we already derived in section 6.4. That's for an infinite space and for outgoing wave boundary conditions. That wave just propagating outside, no incoming wave. What happens if we have an incoming wave? No big deal, we just add a minus here. So if we have incoming wave, don't worry, okay? That's the Green function, x prime. And what is the frequency? Frequency is here, inside the value of k. Okay, it's a hidden. Actually, this Green function is function of frequency. We may solve equation 6.36, this one, in the same way as in section 3.9. That is, we will write the Green function into this form. What's the difference? Looks very similar. The difference just here. Because theta dependent and phi dependent, we can use spherical harmonics. Spherical harmonics YLM theta prime phi prime times YLM theta and phi. GL is function of R and R prime, and GL can be determined from the boundary conditions. Okay, quite similar to section 3.9. We will solve GL for R greater than R prime and R smaller than R prime, two conditions. And under these two conditions, this one is 0. Why? Because that means the source term S does not equals S prime, right? R is greater than R prime, or R is smaller than R prime. So this terms not 0. Therefore, delta function gives us 0. Because if this one, the argument is 0, we will have an infinite value. But others just 0. Okay? So we can simplify the calculation under two extremes. Then we will apply the boundary condition at R is very small, R is very large. Two extremes, as well as this one is not 0. Three boundary conditions. People might expect this one, but we still have the other two. These two boundary conditions are still very important and cannot be infinite, because we will encounter these two boundary conditions. It must be reasonable. must be finite. The result will be gx prime, x prime, 4 pi I k, sum over L equals 0 to infinity, JL, KR smaller, HL, first kind, greater, sum YLM. Okay, so the solution is not just one, but an infinite number. L runs from 0 to infinity. M runs from minus L to plus L. Okay, I don't want to show you how to derive this equation. This is an advanced. This maybe if you want to study the mathematics or if you want to be a scientist, try your best to derive this equation by yourself. If you want to become a rich person or an engineer, all you need to do is to apply this case, apply these conditions. That's what you need. Okay. You just know what is the philosophy for these equations, how to derive this equation, And this one, so when r is very small, r is smaller than r prime. This one gives us 0. Really? Yes, 0. And when r is greater than r prime, that's the source term. This one very, very large. So we have another one. R is greater than, we have Hankel function of the first kind. No matter how, this one will become very large. So this is finite, but this one will be infinite. So this equation will become 0. Makes sense. Of course, we do not check this condition. We do not check the delta function, but just like the previous case, we think it's probably correct. Okay, if you are interested in the derivation of this result, you can check with Jackson. But Jackson quickly goes through this material without detailed derivations. So try to a little bit challenge to derive this equation. Okay, now we will equating these two expressions, this one and this one, for the green function. We obtain this one. This is the expansion of the green function. This equation, this form looks very simple. And this form will help us a lot because we have YLM. YLM will become spherical harmonics like angular momentum and magnetic quantum numbers. So these terms will be very useful. Science is to divide the things into different parts, different categories. And this one looks simple and reasonable. If k equals 0, just becomes the simplest case. Okay, 1 over absolute value of x minus x prime. That's the simplest case. But now we have a propagating wave. So we have a k squared. We have these extra terms. Therefore, it changed to this one plus this one. Maybe you can check your lecture note If k equals 0, what will happen? K equals 0. This equation is quite similar, but of course not this one, not 0. And k equals 0, the solution will be simple. Where r greater, r smaller, and r greater are respectively the smaller and the larger of r and r prime. That means, let me write it down. If, oh, not good. We can erase this part. Just consider this one. So in this case, this one is greater than this one. So obviously this one is here. And smaller is here. Okay. On the other hand, for r smaller than, for this case, r smaller than r prime, so greater becomes here. Smaller becomes here. Okay. That means if we divide it into two conditions, but we use a shorthand notation. We use a shorthand notation, so we have to pay the price. The price is when the notation becomes simpler. We should be careful. We should be careful. Okay, next page. So we will summarize the differential equation and the solutions. We consider source-free first. Let's part 1, source-free. So we have a Laplacian. Laplacian phi equals 0. Helmholtz wave equation, source-free. Happy days. So source-free, we have a Laplace equation, source-free electrostatics. Laplace equation, source-free exponential I alpha x exponential I beta y. That's for Cartesian. And this one will give us a minus, put it into here will give us a minus r squared minus beta squared. So z will become this one. Square root alpha squared plus beta squared. Okay, we learned this one in section 2.9. And for cylindrical coordinate, we have a Bessel function, exponential im theta or im phi, exponential kz. Okay, we learned this part in sections 3.7. And for spherical harmonics, spherical solution, spherical coordinates, we have YLM plus RL, R minus L plus 1. Okay, once again, we learned in sections 3.1 and 3.2. Now we have source, Helmholtz wave equation. Helmholtz wave equation, source-free, time-independent wave equation. Laplacian plus k squared times phi equals 0. So in this case, for the Cartesian, we have ikx, iky, and ikz, ikyy, ikxx, and kx squared, ky squared plus kz squared equals k squared. Okay, that's the simplest case. Okay, if we consider cylindrical coordinates. We have a Bessel function. We have exponential im theta or im phi. We have exponential ikz times z. Okay. For spherical coordinates, we have ylm, theta, phi. That's for theta and phi dependence. We have a Bessel function of the first kind, Bessel function of the second kind, JL, KR, NL, KR. We learned this part in section 9.6. Okay, that's the first one. The differential equation with a point source, we will consider this one with the Laplace equations, with delta function. And the boundary condition is very, very far away, we have nothing. And for Helmholtz wave equation with point source, with differential equation with point source, that's for DE differential equation with a point source. Point source. We have an outgoing wave, and the solutions for the green function for this one, easy, 1/1 divided by x minus s prime. And this one, we have an extra terms here. You can simply substitute this term into here, this g into here, and you will find they are correct. They are 100% correct. Simple, okay? By substituting this part here, we substituting Laplacian, it will work on this one and work on this one. Okay, and work on this one, we have extra terms here. Cancel. So we don't have to worry about this part. You can consider this one as two parts. Two parts. Okay. And the series expansion of the green function is shown here. Many expression. And we have 9.98. Let me show you what is 9.98. This one. Okay. How about the others? Equation 3.70, 3.148, and 3.168. 0.70 is in Cartesian coordinates. In cylindrical coordinates, is 0.148. In spherical coordinates, 3.168. Okay, what's next? We will compare another one. Another two equations. Another two equation is, first is the Helmholtz wave equation. The other is the time-dependent wave equations. In this case, we will consider a delta function in the solutions for cylindrical coordinates, Cartesian coordinates. Okay, just very similar. And for this one, axt, phi xt, we prefer to use a different notation for this one. Axt, so Laplacian g will become this one. Okay, so the solution for g will become this one, delta function. We won't talk about this one. Looks very beautiful, but actually not that easy. So it's a time domain, time dependence. It's a frequency dependence. See, no time dependence. If you perform Fourier transform, you will find this equation or find this equation. Either way. Okay, I don't want to derive this equation again for you, but if possible, you can check your lecture note. It is in the last semester, 6.44. Maybe I should double check. Give up. Let me quickly go through equation 3.70. Open chapter 3 and 3.70. 3.70. Oh. Okay, here is a green function in spherical coordinates. Go back to chapter 9, 168, 168, 168, 168. Oh, here is the solutions for 168. What happened? Okay, 168 actually is green functions. Okay, at least you can check this one. You can check this one. Expansion of green functions in cylindrical coordinates. And for this one, once again we use the same strategy. Similar strategies divided into two parts and then joined together. Okay. So eventually we got this 148. Maybe it's 148, not 168. 148. And another one is the green function. This green function is eigenfunction expansion. 167. 167. What else? 167, 148, 348, 348, 348. Oh, 348 is here. And 3.70, 3.70, 3.70. Oh, here. Actually, it's this one. 3.125. Okay, that's for spherical coordinates. I remember we have more expression. For example, this one. That's for harmonic. Okay, for example, this one. YLM 3.70. This one, once again, we have various expressions for 1 over x minus s squared. Okay, I will stop here. And if you have any questions, you are welcome to call on me without making any reservation during the office hour. Thank you very much for your attention.